Thanks a lot for the introduction, Matt. So welcome to this third webinar focusing on the Magnetics Design Module, or MDM. And in this one, we'll be taking more of a deep dive at an application, which is an LLC transformer and an LLC inductor. Previously, we've held these two introductory webinars to MDM. So the basic stuff that we covered there, we will not cover again here. If you have not watched those, I suggest checking out the recordings of those webinars. But even if you have not watched them, that will not affect your comprehension of this webinar, because we will not be spending time here talking about MDM mechanics, but more just looking at and the results that MDM generates and what conclusions that we draw from that. So this is the overview of our webinar today. We will start with some extremely important acknowledgements. Then we will look at the 600 watt DC-DC LLC converter that we'll be taking a look at here. Briefly go over some LLC design principles, look at an initial LLC design, whether it meets our spec, look how and why to refine it and what we get in the end, and then finally look at some alternative designs, playing around with MDM, seeing what we get. So first, the acknowledgements, which for this webinar are extremely important. We would like to thank Infineon, and especially John Hancock from Infineon, who is a co-author on this application note, and also on this APEC 2020 professional education seminar, for providing most of the material that the next 4 sections of this webinar are based on. All materials are used with permission of the author, and of course Infineon, and you will see on many of the slides an Infineon logo indicating that we have taken a graph or a picture from their material. So let's take a look at this converter. It's a nominal 380 volt input to 12 volt output, 50 amp at full load. So this is a picture of the Infineon demo board, which is designed in the app note. The process of arriving at that demo board is described in that app note. And of course, this demo board is older than MDM as a product, so Infineon did not use MDM to design it, but we can simulate the entire system in SIMPLIS and MDM, and we can see very clearly the rationale behind the design choices that Infineon has taken, and this will illustrate very well how MDM can be useful in such an application, and that's what we're going to do today. So the design specs for this converter were the titanium efficiency specification, which requires peak efficiency 96% at 50% load, and that's for the full switch mode power supply, including the rectification stage, the PFC, and the DC-DC stage, which in our case is the LLC. So allowing a reasonable 1.5% of the efficiency budget for the PFC, this gives us a targeted LLC peak efficiency at 97.5% at 300 watts, which is a half load point. So briefly now, an overview of some LLC design principles and how the design of this converter was approached. So ideally, we want zero voltage or zero current switching, and therefore conduction loss is the main loss mechanism in the LLC. So what we want to minimize are both the RMS currents as well as the component resistances, which are generating that conduction loss. Buck mode reduces RMS currents compared to boost mode, and we also know that in the LLC, the highest efficiency is near resonance. So the consequence of these two things is to pick a transformer turns ratio that minimizes DCM operation and also places the resonance near the minimum input voltage, which is the operating condition which normally results in the lowest efficiency. So we want to put that highest efficiency operating point at the lowest efficiency condition to get that boost. And conventional wisdom tells us that we want to minimize transformer flux and core loss because it contributes more or less evenly across the load range. It does not scale nowhere as near as winding loss as you increase the load current. Some notes on the resonant tank values that were picked for this converter. A high inductance ratio between the magnetizing inductance and the resonant inductance minimizes the primary magnetizing current. A relatively large resonant capacitance gives us substantial power headroom and a relatively small capacitor ripple, making capacitor ESR losses less important. And then using the kind of standard first harmonic approximation method, an LLC tank with 50% margin is derived to be with a CR of 100 nanofarads, an LR of 20 microhenry, and a magnetizing inductance for the transformer of 180 microhenry. Now, in this webinar, we're going to focus on the magnetics design and the analysis. If we talked about the LLC, as a whole, from start to finish, this would take much longer than an hour. So for more details on, the LLC design choices, the selection of other components like the semiconductors, please refer to the cited application note and PE seminar. And even if you don't have access to that APIC seminar, the application note is very detailed. So we can make a nice companion to this webinar if you really want to go through LLC design through and through. So one way to start, and especially an experienced engineer might start who kind of knows what to expect approximately, is to do a loss budget. So even though our peak efficiency is at 50% load, our critical thermal point is at 100% load, because that's where our currents are highest. And there, the required efficiency is 96.5%. This gives us a loss budget of 18 watts. It is expected that the FETs and the transformer are going to have the highest loss component, and initially 3 watts are budgeted at full load for the transformer. So let's take a look at how this initial magnetics design for the LLC was derived. So the spec said that the maximum allowable temperature is 110 degrees and the maximum ambient temperature rating is 55 degrees. So that gives us a delta T of 55 degrees as well. Since the total loss budget for a transformer was 3 watts, we get a required thermal resistance of 18.3 degrees per watt, and this figure pointed to the PQ3535 core, which satisfies this requirement. The coil former for this core shows an RTH of 16.5 degrees per watt, and it's able to dissipate up to 3.3 watts at an ambient temperature of 55. So the core size and shape was selected mainly on the based on the thermal requirement. The next section is how to pick the material in this case, because that PQ3535 core comes in a variety of ferrites. Ferrites have this parabolic relationship between temperature and losses. So meaning that, for example, at low load, where the transformer is not very hot, you could actually get higher core losses, and this can hurt your low load efficiency. So TDK PC95, which is similar to 3C95, which is plotted here, actually has one of the flattest characteristics between loss and temperature, and that's why it was selected for this application, because it makes our core loss across the load range quite predictable. And here we need to meet that spec across an entire load range. So then, standard transformer design equations were applied to come up with the turns ratio given all the things that were selected previously. That's just Infineon slide. I'm not going to go through it in detail. I'm just going to leave it there for your reference. If you've designed transformers before, you're familiar with calculations like this. I'm just going to comment that what we got was a 30-to-2 turns ratio. Now this is a half bridge, so we have two secondaries, so it's 30-to-2-to-2. So when everything was tabulated and when we got the results for the efficiency of this initial design, what is evident here is that while the peak efficiency spec at 50% is being met, the spec at 100% load is not being met. And we have this drop off of efficiency as we approach full load. So to see what is going on here, let's now move into the actual simulation model in SIMPLIS. So again, simulation model kindly provided by John Hancock and Infineon, but built on top of the standard SIMPLIS LLC schematic that you will find in our examples, of course, modified to accurately model all the components that Infineon was using and adjusted to their power level, switching frequency, and so forth. Here we are looking at 350 volts input at 50% load. So when we look at the results that MDM generates after the simulation, here we see the resonant inductor, which has 0.35 watts losses, which is okay. But here we look at the transformer. Now, before we look at the results, maybe let's look at the transformer construction. As we said, it was a PQ 3535 core using PC95 material and a 30-to-2-to-2 turns ratio. The primary is composed of Litz wire. 90 strands of AWG38, and we have a 0.5 by 20 millimeter foil used for the secondary windings, because the secondary windings are going to be taking a high current and we want to minimize the RMS losses. So once we run this simulation, we can examine the inductor. The inductor is based on an RM14 core using N87 material, gapped for 18 microhenry. And in order to reduce proximity loss, tape was added here to move the winding away from the central air gap. What we're seeing here is that the losses are quite acceptable at 50% load, and the winding losses are quite low, and that the proximity effect, in fact, at 0.012 watts is not a huge worry in this design. Okay, so what we can see here, that even though the entire converter was meeting that spec at 50% load, we are exceeding the loss budget that we set, which was 2 watts at 50% load. So already we have a problem here. And the problem is coming mainly from the conduction loss, which is what we had hoped to minimize. But it's hurting us a lot more than the core loss, which is low. So let's take a look at another load condition, which is 380 volts. So the design is the same. We're just now doing 380 volts in rather than 350. And transformer losses are coming up. And if we look at the difference here, we will see that our inductor losses go up a little bit by about 0.1 watts, well, even less than that, as we increase the input voltage. And we can see how here at the lower input voltage, where we picked our resonance frequency, we had a nice sinusoidal, whereas here we have this little notch. It's adding some extra harmonic content to this waveform, and that is one of the reasons that is contributing to this higher core loss, for example. The reason that this takes as long as it does is that for foil windings, rather than treating the entire turn as a single uniform block of copper, which is what we do for round windings, we actually discretize the foil winding into little pieces, which allows us to get a more accurate calculation. So here you can see how the proximity losses, which in this design are very small, but they do show up on this kind of heat map, because this is a relative scale, are penetrating to the surface of the foil and not all the way, because we have done this discretization. So whenever you do foils in MDM or square or rectangular windings, you're going to have a bit of a performance penalty for the simulation. Also depending on the arrangement, because this discretization is determined dynamically based on the size of the foil and the size of your winding window. So some foil winding based, or for example planar configurations may compute a lot faster, whereas some might be quite slow, is what we're seeing here.
We had another question pop up. Is the sim time also related to the thermal modeling?
Yes. So here we are doing thermal modeling, which means that the thermal model assumes a starting temperature to be, a few degrees above ambient, and then it calculates that temperature and then recalculates those losses with that temperature, and there has to be convergence between the assumed temperature and the temperature that comes out of the thermal model. So typically this will take several cycles to converge, and the hotter it is, the longer it takes. This can be turned off by simply assuming a constant temperature, and then things happen much faster. So here we're looking at the transformer design at 380 volts input rather than 350. And here the transformer is actually below, no, sorry, it's not. It's still above our 2-watt loss budget at 50% load, but doing slightly better than at the lower input voltage. I would like to mention one important issue when we're looking at these waveforms, and that is properly setting the frequency and the waveform shape of the waveform of the transformer or inductor being analyzed. Now here you see a kind of irregular or semi-sinusoidal, you might say, shape of the winding currents. So you might be tempted to set that winding shape as being sinusoidal, one or more harmonics. However, when we look at the flux density, we see that the flux density is more or less perfectly triangular. So therefore, when we are setting here in the transformer dialog the wave shape, here it should be piecewise linear, not sinusoidal, one or more harmonics. It will make almost no difference to the analysis of the current, or shouldn't. So don't worry about that. The current we always put through an FFT anyway, but it will make a huge difference most likely on your core loss number. And if you pick sinusoidal, whereas it's a piecewise linear waveform, you're missing out on the more accurate algorithm for core loss that processes piecewise linear waveforms, and you're going to get a core loss number which is likely going to be off. Another issue here is the frequency. Here in the LLC, our switching frequency, or our fundamental frequency of the magnetics waveforms, is changing as we change both the input voltage, the output load, and as we change the design. And we change things like the magnetizing inductance and the resonant inductance and the ESR just of those two components. So it's important to have that number incorrectly. Here in this schematic, we are actually measuring the frequency and it gets output here. So what would be the correct thing here to do is to run one sim with this checkbox disabled. Don't waste your time on running a possibly incorrect post-processing. Figure out what that frequency is, put it in here, then check the box, then click OK. In the future, in an upcoming release, if you're running POP like we're doing here, it's going to figure out the frequency for you. However, you can't always run POP. Maybe you're running a transient. Maybe you're using Verilog or the DLL block and you can't run POP. So I would always make sure that that fundamental frequency is set properly based on what you observe in the simulation, because if that's off, then the FFT calculation for the winding losses is off and you can get some nonsensical results, basically. So finally, let's look at the full load, because that's where we were missing that efficiency target. And let's see what happens here. So we can see that at full load, now our inductor loss has gone up to 0.86 watts. And again, as we're waiting for these transformer results, I can open the floor again for questions.
We got one come in here. Does the core loss change the inductance value of the transformer?
No. In any case, we can say that the core loss is calculated in a post-processing step. So what we have in the circuit schematic is just the DCR of the windings, just the winding DC resistance. And that is what is affecting your circuit waveforms. There isn't like a resistor put in there, for example, to model the core loss. That's highly nonlinear. So inside the schematic, we have the DC winding resistance of the inductor and of the transformer for each winding. And we also have the leakage of the transformer. But then we calculate all the other losses, the high frequency winding losses and the core losses in the post-processing step.
We had another question come in. How do you calculate the inductance of the inductor and transformer?
We calculate it based on a reluctance model of the core. So we would divide the core up, and for each core shape, we have our own model of a magnetic circuit or a reluctance circuit. So we would divide the core up into sections for which we can reasonably assume to have homogeneous flux density. This gives a small number of sections per core, something like 6 sections per core half, or it varies based on the core shape, but it's in that range. It's not like 50 or 100 or something. It's in the single or low double digits. And then based on that, we calculate the total reluctance of the core. And then, of course, using the number of turns, we calculate the inductance. So we use the initial permeability of the material defined in the database to get that one number, which is displayed here. But then we use BH curves or μH curves or whatever happens to be available for that material to calculate this L versus current plot. And we calculate the plot up to the maximum flux density. For example, for this inductor, you're not ever going to operate it near 200 amps or 150 amps, but if you just take that geometry and see what current you're getting at Bmax, that's what you're getting. So that's why it's on the characteristics. We can see here that our peak current is about 5 amps, and if we zoom in on our L versus current characteristic, we can see that, you know, we are far away from saturation here, even at double that, at like 10 amps. Okay. And here are our results. So I'm going to remind you that our loss budget for the transformer at full load was 3 watts. And here we have almost 6. So we have 5.835 watts. Following the conventional wisdom, you know, core loss was minimized, but we have this rather large AC conduction loss, even though we're using foils. So the question is, what can be done here to improve this design? And let's go back to our slides. So that was our loss budget. So 3 watts is what we were aiming for. And what came out from this initial pass was 5.835 watts. And this is one of the main reasons why the spec is not being met at full load, where it's our critical thermal point. So how to refine the design? So if we look at that curve that we saw here, there is space at light load to basically reduce the efficiency. Red curve is our target, blue is what the first design got. But we have to rebalance somehow those efficiency numbers to move the high load efficiency up. So we can rebalance the transformer to increase core losses, actually, which is contrary to what conventional wisdom might say, but decrease winding losses. So because we have space at that low load condition, and because core losses are more steady across the load range and are quite small, as we can see, if we can increase core loss less than we decrease winding loss at full load, then we have a chance at meeting this spec. We can reduce the conduction losses in the inductor by decreasing the winding length. And what do I mean by that? So if we look at the inductor, as I said, the proximity effect, which is why we have this tape here, is not really that big, and the AC conduction loss is much higher. So that's coming from the length of this winding, because if you put extra space in between the bobbin and the turns, you are increasing the length of this wire. So maybe we can try accepting a bit more proximity losses, which don't seem to be very problematic in this case, in order to reduce the length. And finally, there is something which in the app note is called the RMS factor, which is the amount by which RMS current is larger than the average output current. And you want to reduce that in order to reduce your RMS current and reduce your conduction loss. And if you refer to the app note, you will see that increasing the switching frequency will actually do that. So what was done here? And let's take a look at the simulation model. So let's focus first on the transformer, which is the big. So what, of course, the designers of the demo board did was go back to their drawing board and go back to their equations and figure out that a 16 to 2 rather than a 30 to 2, 16 to 1, sorry, rather than a 30 to 2 turns ratio is better for conduction loss. Why? Because you are reducing the winding length and having the resistance, because now you've reduced the number of turns by 50%. That necessitated some redesign in terms of the air gap and some rebalancing in terms of the value of the resonant inductor. But what we have here is now 16 turns of Litz wire and made by Filer. So this is further reducing our conduction loss. And we have a shorter foil. So when we run this now, which should take a bit faster, take a bit less because we have less foils to take a look at. Now, we can look first at the inductor. So that was that operating point previously. So the inductance has been decreased a bit by going to a slightly smaller core. So from an RM14 to an RM12. And what we got are smaller core losses. That's because the flux density peak stayed approximately the same, but with a smaller core volume, we have less losses overall. This would be not the same as if we had the same flux, not the same flux density on a smaller core. Then our flux density would go up and then our core losses would go up, but that's not what happened here. Because of a smaller core, where we also pushed the wires all the way to the bobbin, so eschewing this tape, which is reducing the proximity loss, we had a reduction in the winding length, which we can see here in this inductor design details tab. So the winding length for the revised inductor design was 475 millimeters, and for the original one, 583. And we can see that that reduced our RDC. And even though we paid the price with a bit higher winding losses, proximity losses, our overall winding losses are in fact lower, and our core losses are lower. So we've decreased from 0.35 to 0.229 watts the inductor loss at this operating point. And here we have the transformer results. Let's compare them to the original. Now much closer to our 2-watt target at 50% load. The losses have been reduced by 1 watt. And even though we've increased the core loss by quite a bit, and now it's taking up the majority of our transformer loss, by reducing the length of these windings, by pushing them closer to the core, we've managed to decrease our AC conduction loss quite significantly, as you can see here. So to save time, I'm going to just jump to 100% load at the 380 input and see the improvement at full load now. So let's look at the inductor. At full load, we have a reduction of about 0.3 watts, which is 0.32 watts actually, which is not bad. It's helping us reach that full load spec. And as we wait for the position, here are the transformer losses. And now we can see that whereas previously we had 5.835 watts losses at full load, now with the revised transformer design, we have 2.659. And I would like to point out that if you kind of take a look superficially, you might say, well, these two designs are not that different. We have Litz primaries, we have foil secondaries, we have the same core. And this is where MDM really shines. So, you do that first iteration design. You're following, the best principles. You're following your experience. You're following what conventional wisdom says, should be done in this or that case. And you're very close. And you're missing that efficiency target by 1% or 2%, and you have this extra few watts that you need to get rid of. Rather than having to go back fully to the drawing board and redo all your equations or all your spreadsheets and whatever, right here in MDM, you can just say, well, what if I reduce the number of turns by 2? And you can do that in a few seconds. And you can rerun that simulation in a minute, and then you can see immediately what the result is. So let's kind of recap what was done here with the final design. So the transformer changed from 30:2 to 16:1 turns ratio, having the winding resistance. Core loss is now the majority of the transformer loss, but the total loss is lower. A slightly larger magnetizing inductance giving slightly smaller LR and a lower inductor loss. The switching frequency was increased, and something we're not covering in this webinar, the semiconductor area was increased as well to lower conduction loss. You can look that up in the cited materials. And the final result, what we're looking here is the green line, is that this meets the spec not quite well. So finally, let's look at some alternative designs based off of this, where we take a look at what else we could possibly do. So one option that I took a look at was to change the inductor, because the transformer was already pretty well optimized, but I thought maybe the inductor could work. So there's a lot of decisions that go into picking your core. It's not necessarily what is the best core or what is the cheaper. It might be what you have at hand. Maybe you have to source those RM cores, but you have a bunch of ELP cores. Maybe the ELP cores are a better form factor for the board you're trying to do, for example. So I said, let's try, say, an ELP 32 core, and Litz wire is expensive, so why don't we do just a regular wire and just fill that with copper, because I want to reduce my conduction losses. So I pick an AWG 12 wire, fill that window, gap it so I get the right inductance. I'm still looking at 14 microhenry as I had before. And let's see what we get here. And what we get is pretty terrible. Whereas our core loss is really low, our conduction loss is also quite low, but our proximity loss is terrible. And this is, giving us, this is an unacceptable design for this spec. I mean, 8.6 watts losses, it's insane. And you can see why, because we have this big air gap, and we have 3 of them, and that's just, those proximity fields are just, they're just doing the damage there. And even though we pick a big wire, we fill the thing with copper, we have a low RDC, but the proximity loss is just criminal. So, you know, we have to chuck that one out the window. But we could try a different one. So, sticking to an ELP core, the ELP32, but let's reduce that air gap, because that is really what killed us there. Reduce the number of turns, still use pretty big wire. Let's see what that gives us. And also here, I tried modifying the transformer as well. Now, my initial idea was that I wanted to get rid of these foils because I thought foils are expensive. So let's try using solid wires, multifilar. But this transformer was optimized so well that no matter, you know, what I did trying to get rid of the foils, it just made things really, really, really worse. And maybe I could do, you know, 4 watts instead of 3 watts or something. But so I thought, let's keep going in the direction that the Infineon designers went. And I said, well, let's try reducing that conduction loss even further. Why not make this foil, which in this case, in their case, was 0.5 times 20 millimeters. Let's make it 1 millimeter by 23, assuming you can get a 23 millimeter foil length, because that just kind of almost fills the winding window, but assuming you could. And 1 millimeter thickness is something that's available. So let's see what happens here. So the first thing we notice is that now our revised alternative inductor is no longer terrible. By reducing that air gap, we have cut down the proximity loss by like 10 times. And now we have something that's acceptable, 1.306 watts. It's still not as good as the RM design, which I'll find here. Let's check if that's the current one. Yeah. So it's not quite 3 times worse in terms of losses, but a bit under a watt increase here, 0.8. But what we do have here is that it's a smaller inductor by volume, so maybe that's something you want to trade off. And it's using regular wire rather than Litz wire. So is there a cost trade-off there? That would be up to, you know, the engineer to figure out. But it seems like a amount of losses that would not be terrible to trade off for something else, especially because that efficiency curve shows that now we have more space. Let's look at the transformer. So here, we've increased the foil height and its width, we've doubled it. And did that result in an improvement? Yes, it did. So we went from 2.659 watts to 2.43. So we doubled, more than doubled the area, but our winding loss didn't exactly half. Why? Well, because we've added extra area, now we need extra length for all those wires that are wrapping around the center of the core, so that there's no free lunch in that respect, and that is increasing our resistance while the extra cross-sectional area is decreasing it. And what we then get is a slightly lower loss number. So again, that's something where you would try to trade off whether this decrease is worth the increased cost of more copper here and longer wires. And then finally, I thought, why not go all the way and increase the copper area as much as I can. So the inductor is the same. Interest. And again, it's taking a bit longer because we've increased that foil area, and now we have to spend more time processing it. And now, so going from a 1 millimeter foil to a 1.5 millimeter foil, so increasing that foil thickness by 50% has only gained us 20 milliwatts of improvement overall. And again, it's because we are increasing the length. So we're getting diminishing returns here, and you'll probably conclude that taking into consideration cost and everything, that going to 1.5 millimeter is really not worth your time. So let's go back to our slides. And recap. So magnetics are often key to meeting efficiency targets, especially in a complicated design like an LLC. And an initial design created by a combination of conventional wisdom and practices and experience will hit close to the target. But this is where using kind of pen and paper, where you might waste a lot of time trying to hit that last 1 or 2% of efficiency, or to squeeze those last few watts of losses. And this is where MDM really does its magic, because you can use it to quickly evaluate modifications to the design. You saw that our simulations, despite having to rerun them all, only took a couple of minutes. And so using MDM, the optimization phase of the design can be much, much shorter. And on top of that, the detailed MDM post-processing results allow us to analyze the trade-offs between designs, see why a design performs better or worse, and why and in which cases the conventional wisdom may be off the mark. So when you get, say, a counterintuitive result, you can immediately see where that's coming from, and you can explain it, hopefully. And we can, of course, because we are in the simplest circuit simulation, we can immediately see the effects of modifying the magnetics on the rest of the circuit, and vice versa. You know, you change something in the semiconductors, you change something in the cap, and you see the current or the frequency is changing, and you see the change in the magnetics. So you can quickly go back and forth. That concludes this webinar. Thanks for watching and listening, and I'll leave it over to Matt now to wrap up.